Hi guys, this is Ajit from SVC and I belong to EC department. So today's topic is 5 variable K-map and the subject this is related to is BSDV. Let's get started. So the introduction to this topic, which is 5 variable K-map, goes by. So 5 variable K-map is also known as a 5 variable Karnaugh map. It is a graphical method used for simplifying Boolean algebra expressions with 5 variables. So if you can see here, there are two K maps available here, which is in 4 into 4 state. So this is a powerful tool in digital logic circuit design for dynamizing logical functions and reducing the complexity of circuits. So the 5 variable K map consists of 32 cells arranged in specific grid pattern with each cell representing a unique combination of input variables. So the first step here in 5 variable K map is understanding the grid pattern. Here, the 5 variable K-map grid is organized into 5 rows and 6 columns, each row corresponding to unique combination of 2 variables and each column representing a unique combination of 3 variables. So the cells in the K-map are grouped in a way that each cell is adjacent to the cells that differ by only one variable. This adjacent property is crucial for identifying grouping by terms in K-map to simplify the Boolean expression effectively. The second step here is grouping. So the grouping in a 5 variable K-map involves identifying and circling adjacent cells that contain a 1 in order to form groups of ones. Here, so the groups are created in a way that each group must contain 1, 2, 4, 8 or 16 cells, as these are powers of 2 that ensure optimal simplification. The goal of grouping is to convert as many as 1 cells as possible while forming the largest groups possible for simplification. So the grouping is done as 1 or 2 or 4 in whole or 8 or the whole thing 16. The third step here is handling the don't care terms. Here the don't care terms are additional inputs that specify specific combinations of variables where the output value is not crucial or critical. In a 5 variable K-map, don't care terms can be used strategically to help simplify the Boolean expression further by including or excluding them in the grouping process. Don't care terms provide flexibility in optimizing the logical function by allowing for different combinations of variables in the simplified expression. For example, we can see that this is the representation of a don't care term. It can be grouped like this. This is a don't care term with 1. Can be also excluded like this. Here, this specific don't care term is excluded, and so this is the strategical implementation of considering or non-considering a don't care term. The fourth step is implementing the simplified expression. Once the groups are formed, the simplification process is complete. The simplified Boolean expression is to be derived from the group terms. Here we can see that the simplified term has been derived and the solution is yet to be derived. The simplified expression obtained from the 5 variable K-map represents an equivalent logical function that requires fewer gates in the digital circuit implementation. So we can see that the simplified equation, which is f equals ab plus a bar b plus ab bar, is simplified to a plus b. This implementation This simplified expression leads to a more efficient and optimized design with reduced complexity and improved performance. Application of 5-variable K-map in circuit design. This 5-variable K-map is widely used in the design and optimization of digital circuits, such as combination circuits or sequential logic circuits. It helps designers to reduce the number of logic gates, minimize propagation delays, and improve overall efficiency of the circuit. By leveraging the power of 5-variable K-map, designers can create compact and cost-effective circuit implementations for various applications. So the 5-variable K-map has some challenges and limitations. One of the challenges of using a 5-variable K-map is that as the number of variables increases, the complexity of the map and the number of cells also increase significantly. Handling a large number of variables in a K-map can sometimes lead to more complex and difficult simplification process. Additionally, the manual construction of a 5-variable K-map for a large number of variables can become time-consuming and error-prone. So there are these advanced techniques for 5-variable K-map simplification. To overcome the challenge of dealing the large number of variables, there is this advanced technique called gray code, which can be employed. Grouping variables pairs allows for simplification of larger K-maps by treating two variables or a single variable during the simplification or grouping process. Utilizing this gray code is a binary numeral system where two successive values differ in only one bit. This can be pretty organizing and simplifying these larger K-maps efficiently and effectively. There are some real-world examples of 5-variable K-map usage, which is the 5-variable K-map is extensively used in design of microprocessors, memory circuits, communication system, and other complex digital systems. In a microprocessor design, the 5-variable K-map helps in optimizing arithmetic and logic units, which is ALU, the control unit CU, and data paths for improved performance. Memory circuits benefit from the efficiency of 5-variable K-map in reducing power consumption, enhancing speed, and ensuring reliable data storage and retrieval. There are some tips for effective 5-variable K-map utilization. When working with a 5-variable K-map, it is essential to carefully analyze the input variables and identify the redundant and overlapping terms for effective and efficient grouping. Utilize don't-care terms conditions strategically to amplify the Boolean expression further and optimize the circuit design. Practice creating the simplifying 5-variable K-map regularly to enhance your skill in digital logic design and improving proficiency in circuit optimization. As a conclusion for this topic, the 5-variable K-map is a valuable tool in digital logic design and simplifying complex Boolean expression with 5 variables. By leveraging the grouping and simplification techniques of the 5-variable K-map, designers can optimize the circuit implementation and reduce the complexity and enhance performance. So you can master the use of 5-variable K-map so that you can create cost-efficient and reliable digital systems for a wide range of applications. Thank you.